Welcome back, everybody. I hope you had a good lunch, and I hope you have a lot of energy for the afternoon, because trust me, you will need it. This next talk is something very, very special. It's going to have so much content that we actually need 3 people to deliver it. Please, somebody laugh. Now, in the morning, we once had the question how we handle student tickets and if we have certain discounts and such. Well, of course we do. So if you're a student and you want to come to KCD Austria next year, just drop us a line, we have discounts. But for the very best of them, we even have them as speakers, such as the 3 guys next to me. For those of you who are not aware that the host on the other stage, Constanze, she's actually Professor Rödig. She's a professor at the University of Technology in Vienna, and these are 3 of her students. They're presenting one of the most sophisticated security talks you're going to see at the whole event. So please give me a hand for our 3 guys, Josef Taha, Tobias Grantner, and Lukas Mahler.
Thanks, Daniel, for the introduction. It's great to be here today. And yeah, the next minutes we are going to introduce you to the Kubernetes Storm Center. It's an open source project which aims at simplifying the collection, the analysis, and the shareability of threat data in Kubernetes environments, of course. And yeah, Tobias, Lukas, and I joined this project about 6 months ago, and we're excited to show you how you can benefit from the Kubernetes Storm Center in order to gain deeper insights into cluster security and Kubernetes threats. So the Kubernetes Storm Center provides us with 2 main stacks. The first stack is the honey cluster stack, which simplifies the setup of honey clusters. For those who are not familiar with honey clusters, they are essentially just clones of your production system, which run independently. And the aim of this honey cluster is to mimic the production environment and to perform attacks and tests on them, assuming that everything that runs through on the honey cluster will also run in production. Now, in order to get such a honey cluster up and running, the first step is to clone your production system. Here it's advisable to remove all sensitive data out. The next step would be to use this honey stack we provide and to deploy it on the cloned cluster in order to provide all necessary capabilities, such as the log collection and using tetragram policies and the baseline filtering in order to remove unnecessary system calls and system logs. Now that your honey cluster is up and running, the fun part starts where you can attack your honey cluster yourself to get some insights, or you make your honey cluster publicly available in order to let the bad guys do the work for you. And by observing the logs from the honey cluster, you can gain valuable information. And by utilizing the second stack we provide, which is the threat intelligence stack, you can get much more valuable threat intelligence out of this raw data. Because this stack provides you with capabilities and functionalities like attack detection in logs and visualization and more. And the best part is that all these results can be shared by pushing it into a public threat intelligence database. Now, I have previously mentioned the threat intelligence stack and mentioned that it has attack detection capabilities. And that works by using these attack models. On your left, you can see such a simple attack model, which consists of just one attack step called token theft. And there is an indicator, token SSRF indicator, which is mapped to the attack step, and the indicator basically tells us how a log should look like in order to be associated to the specific attack step. By applying this attack model on the honey cluster, you basically tell the honey cluster that we are looking for logs that matches the indicator. And when the honey cluster detects such logs, it maps it to the attack. On your right, you see such an observation, such a detection, how it would look like. So in our case, the honey cluster has detected 5 logs, which are the blue balls. And yeah, now we know these 5 logs are part of the token theft. Here I want to note that all the logs, the attack models and indicators, they are all modeled in STIX 2.1, which is a standard for cyber threat language standard. So this basically means that we cannot just only share the logs and the results, we can also share the attack model so that others can deploy these attack models on their honey clusters and check whether they detect the same attack we did. But for now, we need much more contribution on that in order to gain a stack of these attack models so people can use them. Now, in this example, we have a pretty simple attack model. Well, things look different in real world where we have much more complicated attacks. And here we can see such an attack model which we modeled and which we gained, which we detected on the honey clusters. In this example, we have a container escape in Kubernetes, and yeah, it can get very complicated. Now, as every project nowadays needs to include AI, we did too, but we did it wisely by utilizing LLMs in order to assist us in 2 tasks. The first task is to identify the malicious logs out of a bundle of log, and the second task is to generate these indicators I talked about before, based on malicious logs. And more on that, Lukas will show you in a demo. And yeah, mentioning demo, now we'll switch to the examples and to a live demo where we have the red team, Tobias, that is going to attack a honey cluster running currently on a GKA. And Tobias, on the other hand, will play the blue team that is observing the attack and responding to it. Yeah.
Okay, thank you, Josef. So, as Josef has mentioned, we have prepared an example application which is vulnerable to SSRF vulnerability, which I'll explain a bit in detail a bit later. But this is basically a simple user application which is running on a Kubernetes cluster, which is running in the Google Cloud. And before we go ahead and destroy some things, I want to show you what the application should do in theory. So we basically have just deployed a simple user service in a Kubernetes cluster in Google Cloud. And when the user service is started, for example, it needs to access some secrets, for example, to encrypt the session token. And it is configured via a service account, which has access to the Google Secret Manager. And it gains access to the Secret Manager by requesting an access token via the metadata API, which is only accessible from within the Kubernetes cluster. This is very simplified, but the metadata, upon getting the request for a token, basically just checks, does this pod actually have the access to the secret manager, and if it does, and it gets a checkmark, it returns the access token, and with that, the user service can request the value of the secrets it needs. And user interaction with the service could look like this, for example, via image upload to change the profile picture of a user. For example, the user could provide a URL pointing to an image hosted on a server, send this to the user service, and the user service requests the image from some server and encodes the result, sets it as the new profile picture of the user, and returns the new profile picture back to the user. Now, let me show you the demo live. And for that, I will put on my red hat for the red team. And yeah, so if you go to the page, you're presented with a simple login, which you probably use every day in some applications. And we go ahead and enter my username foo and the password bar. This is the password I use for all my accounts, so please don't tell anyone. And then once we're in, we are presented with our user's profile. And here you can see some information about the user. This is similar to many applications, and some profile picture. And if we click on the picture, what you can see is a prompt to either choose a file locally to set this new profile picture, or to provide a URL pointing to an image. And the security experts among you might already see where this is going. I've talked about the metadata API, which is only accessible from within the cluster. And if we go ahead and specify the URL, which can be used to access an access token, and press on upload, we can see that the profile picture has now changed, and it can't be displayed anymore. And if we go to the developer console and look at the image source, we can see that it is now set to a data URL, which includes some base64 encoded data. And if we go ahead and decode this data, we can see the JSON response of the token endpoint of the metadata API. And in here, we can see an access token and how long this access token is valid. And from that, we can extract the access token and copy that. And I've prepared a simple script which just accesses the secret manager in Google Cloud with the token we have in our clipboard. And if I go ahead and execute this, we can see we have successfully retrieved the secret value, which is a very secret. And by that, we were now able to access the secret manager outside of our cluster. And obviously, this is quite bad, right? Because inside of the cluster with Kubernetes Storm Center, for example, we can detect what people are doing and maybe catch them doing something bad. But once someone gains access to such an IAM access token, we can't really detect what they're doing with it. And if we can detect it, for example, in some logs of Secret Manager, then it's likely too late because the person already accessed the secret. So that's similar to your house key getting stolen. You don't want to wait for someone to empty your home, right? You want to change the log before anything bad happens. And now let's look at what exactly happened here, or how this was possible. So we made use of a server-side request forgery vulnerability in our application, where the user sent a profile picture change request, and instead of a valid URL pointing to a picture, it sent a malicious URL pointing to the metadata API. The user service failed to check that properly and requested the token from the metadata API. And the metadata API, this is important, cannot distinguish a valid request to one initiated from an attacker. So it got the token back, thinking it's an image, encoded it, set it as the new profile picture, and returned it to our attacker. And after that, the attacker is able to request the value of the secret outside of our Kubernetes cluster. And now we obviously want to do something about this. And in order to do something about this, we have to catch the token theft, because after that, we're kind of in the dark. So how can we detect such a token theft? We have to always find two things. We have to have a malicious user input, which triggers the token access, and it looks completely different based on which applications you have deployed in your cluster. And the second part is a valid token request, which generated or accessed the token. And depending on your cloud provider and your your settings you set in the cloud provider, this could either be a HTTP request, which we just saw, or a file access, or reading some environment variables. For example, in GKE, by default, it's an HTTP request, and in AWS, it would be a file access. But you could also change the settings in GKE to provide it via a file. So the point I'm trying to make is you have to test this out in your environment in order to see what such an attack could look like for your specific setting. Now, this sounds like a lot of work, right? And if you test this out, you produce a lot of logs, and from these logs, you have to find some pattern which matches the attack. Is there any way we could make this easier for Lukas?
Yeah, fortunately, there is one way. So fortunately, the attack that was done was on a honey cluster. So this means all our instrumentation we've already talked about was already in place. What you've seen in the first demo is the left part of this graph. So the attack was done, some logs were produced. Fortunately, we are now collecting those logs and can then try to find those potentially malicious logs. And when we found those potentially malicious logs, and we know, okay, they are really malicious, then we can also try to catch them automatically via an indicator that we'll create. So this will look something like that, maybe. So we try to catch this attack now in the next part of the demo. First of all, we of course have to download all the logs that were just produced. Yes, so nice. Now we have our logs in the temp.sticks file. This we can then load in a notebook, which I've already prepared. So we load all the data, and what we are doing here is we create a prompt where we say, okay, what are we looking for? And then also add, of course, those prompts at the bottom here. What we are searching for is, of course, the log. So we go by ID. We want to have a message, a description about, okay, what is happening here. And then, of course, also an explanation where the LLM thinks, okay, this could be malicious or this could not be malicious. Yeah. Once this prompt is then completed, then the next part would be to find those two logs we're searching for. You already see it from the last execution, how something like that could look like. Because once we have those malicious logs, we can then write them to a file and then go on to the next step where we try to catch those logs, those malicious logs. So hopefully the LLM will be fast today. Yeah. Maybe a bit more in detail. Yes, okay, we have it already. Let's look at it. This is the output of the LLM. Let's see what it got. Okay, here the first one, maybe you can already see it, the fast ones. This is the token request to the metadata API. So this is the first part we want to find. This is exactly the request where a valid token request was done. This alone doesn't mean, okay, there was an attack happening. We only know, okay, a valid token request was done. But in close proximity to this request is another one. So let's go into the log. Hopefully the LLM detected it as well. Yes, here is the other request we are searching for. And this is the SSRF attack. Maybe you see it already there. The metadata google.internal URL was called via this SSRF attack. So this is the next log we want to find. So good. Opa. Okay, never mind. Let's do it. Yeah. So good. Now we have those two. Let's double check if the LLM really did find those logs we were searching for. So let's go to the messages. And we are seeing, yes, exactly. This is the token request. And the next one, yes, this is the SSRF exploit. So now that we found those two, let's write them to a file. Nice, this was done. Then we'll go on to the next notebook, where we are trying to create the indicator. So we know now, okay, those two malicious logs we're searching for. And now we say to the LLM, okay, please try to catch it automatically. It will create an indicator. Especially the most important part here is, of course, the pattern that defines, okay, when do we want to match some logs? And this could look something like that here. So you see some description, what we are trying to catch, and then most importantly, this pattern here. So we say here, okay, this log we are searching for, this is an artifact, and the message has to match, first of all, the token request, and the second part here that you can also see here is the call to the metadata. This is the SSRF attack with the metadata Google internal URL in there. Then we, of course, add some other information that Sticks needs to be valid with the specification. And what we are getting out is a valid indicator, which we could, for example, upload. Of course, you usually want to adapt those patterns. So this is the reason why we say, okay, we don't let the LLM do everything for us. We say, okay, you get some idea of how it could look like, but you usually have to adapt the pattern and stuff like that until you're happy with it. This could then look something like that. This is a prepared indicator we have written, so similar to that one you have just seen, but we did some manual intervention and created the pattern as we wanted, which we then, of course, can upload to our honey cluster so that the instrumentation in the future is then set up. This honey cluster is pretty much armed for this attack, and in the future, when we get such an attack, then we can automatically match it. So this looks something like that. This is the indicator here. This is in Neo4j, so this is pretty much where every matched log ends up. Here the indicator, you already have seen some screenshots previously about Neo4j, and you see here this indicator is for now alone because no attack has been happening. But how would it look like if some attacker would attack now?
Yeah, let's see if you can actually catch me now. So in order to see if we can, oh no, if we can now detect a token theft, actually detect it and do something about it, I will attack our application again by, again, triggering an image upload, again with the malicious URL pointing to the where the token is requested and pressing upload again. And if we look at the response again, just like before, there's some data encoded, and if we decode it, we can see, okay, here we actually have, again, requested an access token, which now it's the same token as before, that's why the time to live is shorter, and we can, again, extract it. So, did you catch me, Lukas?
Yeah, hopefully so. So let's do the query again, and let's see if we find something. Oh, yeah, looks quite different now. And what we can see here is the indicator once again in orange, but also now we have some more information. And this exactly are those two logs that were produced, this one and this one. And if we look at the message, then we can see once again, hopefully, yeah, exactly. This is the token request, which was triggered by the other one here. This is the SSIF attack. So we could successfully then catch this attack. Good. Now that we know, okay, we can catch it, we can, of course, put some countermeasures in place. For example, here we could just disable the service account, and then the attacker should have no chance anymore. Let's try it. Good. The service is disabled, and when the attacker attacks again,
yeah, and now we do the same as before. We use the token we just requested and try to get access to the secret again. And now we're seeing an error because our token is not able to access the secret manager in Google anymore. And yeah, so now we've shown you that we are able to detect such attacks successfully and are therefore able to counteract attackers who gain access to such a token by some vulnerability in an application to do damage on our clusters or on our cloud infrastructure. But to sum up, the point we're trying to get across here is that this is one example of such an attack. But if you have some other application deployed and use a different cloud provider or a different settings in your cloud provider, this could look completely different in your case. And there's no one-size-fits-all solution. But we're trying to make it as easy for you as possible in order to find out what such an attack could look like in your environment so you can protect yourself against it.
Yeah, and now that we're coming to the end of the talk, we would like to give you the lesson we have learned throughout this project. And it's that when you're able to make an attack visible, to be able to see the logs that are produced by the attack, to see how such an attack could look like, and to be able to then perform the attack yourself on your honey cluster, you take the fear out of these threats. And by that, I would thank you very much for listening. I hope you enjoyed the demonstration and the talk. And we are actively looking for people who are interested in this project. So if you want to contribute to it, or if you have some feedback, we would love to hear from you. Yeah, Thank you. Do you have any questions?
Any questions out there? Yes. Over there. Friendly reminder, we have gummy bears. So if you're into Coke gummy bears, raise your hands. I want to get rid of them all. There's 100 left. Question over there, question over there, question over there. Yes, 2, 3, 4. Amazing.
Hello. So you mentioned that all of this is pretty open, which is great, especially for something concerning security. My question was about how those models that you showed on the CRSRF attack, or what was it again now? How are they shared? As in, do you need to make the models of attacks for your honey cluster, each individual, and there isn't really a framework to share each kind of attack, each vector of attack? Or is there an open database that everybody contributes to and can pull from with some?
So if I can answer this. So currently we don't have an open database yet because we don't have enough contributors to the project. So that's why we need a lot of people to deploy some honey clusters and to see what they can achieve with it in order for us to all be able to work together. But the goal is to eventually build a database where you can share on one side the models, which we showed you an attack which looks completely different in different scenarios, but this is not the same for all kinds of attacks. So you are able, for many attacks, you are able to reuse the models, and for that you can share the specification of an attack model, so someone else can deploy it in their cluster and is able to then detect these kinds of attacks. And then on the other hand, we want to make the knowledge you have gained by deploying a cluster with some models shareable, so everyone can benefit from the insights you have gained. But we're still working on that part.
Thank you.
I think I've seen some other questions over there as well, didn't I? Yes, no, didn't forget you. No.
I think you partially answered my question already, but what I wanted to ask is why you are deploying to a honey cluster and not to an actual live cluster.
Yeah, I mean, that's a good question. Ideally, there are two benefits of this system. You can either attack yourself and see what you can find out by that, which we have just shown with the red team and the blue team. But another option is to open this cluster up to the public and just find out which attacks people perform on your cluster and learn from that. And with that, you don't really want people to be able to destroy your production cluster. So you copy the cluster so it looks real, so people get an incentive to attack it, but they can't really do any damage.
But I might not be aware of the vulnerability in the application. So if I deploy your stack to a live cluster, in case an attack happens, I would get alerted, right?
So this is not the goal of the project. We don't want to do live attack detection in production clusters. It's more about gaining knowledge about known vulnerabilities, for example. So,
and if enough people then contribute, then you can see, okay, this attack is really exploited right now, for example, by 3 honey clusters. And then you could, because you always have a backlog of CVEs and stuff like that. But if you can see, okay, this CVE is really exploited, then you could rank it more up for you if you can't get rid of the application that has this CVE, for example.
Yeah. Okay, thank you.
Very interesting, thank you. I'm really not sure how really shareable this may be in the future, because if you already also take into the view the trace path, how an attack comes along, there might, of course, multiple different paths between companies. So this is just for one kind of log files. Pardon. Have you any a future interest in going further, how to share a model with different trace paths? Or have you experimented with it?
Of course, the stick specification which we are using allows to do something like that. You could match an attack pattern in very many different ways. So you could have multiple indicators indicating the same attack, but maybe on a different system, something like that, for example. So this should already work more or less out of the box. But what we are, of course, missing currently is a public database where we can upload those sticks logs, or indicators, attack patterns, and of course, maybe also the observables.
So I think we have time for one more question. Anybody? Yes, over there, please. Where's the mic? Just a second.
Thank you. Thanks for the talk. Interesting project. I have two questions, actually, rolled up into one. The first one is, would a WAF prevent such an attack? And why not collect logs from the WAF? Because application logs can be very noisy. I've known developers that like to enable debug mode. So yeah, that was it.
Okay. For that, so that we can reduce the logs, which wasn't too much part of this talk, is we create a baseline. First, before you open the cluster to the public, you let those services you have running, and then you create a baseline based on that. And we then do a more or less, you can think of it like an SQL join, where you then only keep the new data, which didn't appear in the phase where you had those benign traffic. So we are already reducing the logs by quite a lot.
And maybe to add to that, we reduce the logs by creating a hash based on some attributes of the logs. So we collect a list of hashes we've seen before to fingerprint basically the logs. We know that they are benign, and so we filter these out before processing them further. So by that we are able to reduce the amount of data by quite a lot already.
And another part, of course, is you can set up the tracing policies how you want them. If you know, okay, something produces really many logs, then you try to create a tracing policy in a way that you don't get the service in, or just some parts of it. Yeah.
Thank you.
All right. Thanks for listening. If you have any further questions for these guys, they're going to stick around. I'm pretty sure of that. Have a coffee with them, challenge them. They still need to earn their master's degrees, so make it worth the while. See you back in 10 minutes with the next talk here on Hall 6.